Dear students, today we are going to discuss about simple harmonic motion. Okay, this is a part of the last module. We have seen rotation, then we have seen translation, curvilinear translation, all those things has been seen. Now we are going to see the concept of simple harmonic motion. So through this we are going to discuss about what time period is, what is the frequency, what is mass, what is stiffness. All those things are going to be get discussed in detail through this video lecture. So in the beginning, let's see what simple harmonic motion is. Okay, so what is it? That's the very first thing we want to know. When an object moves to and fro or back and forth along the same line, it is called as simple harmonic motion. Okay, so it basically tells that when an object is moving back and forth in the same line, we call it as a simple harmonic motion. For example, a fan is rotating, so the path the fan follows is the same. Okay, it is going to follow the same path, so it is also called as a simple harmonic motion. So the definition is available here. The simple harmonic motion occurs when a particular object moves back and forth within a stable equilibrium position under the influence of a restoring force proportional to its displacement. Okay, a restoring force proportional to its displacement. Okay, you might have remembering the spring. What is the force in spring? Force in spring is K times X, F equal to Kx. That is the equation that you learned when you were in school. So F equal to Kx, which means that force is proportional to displacement. That is the last part of the equation, the restoring force proportional to its displacement. Okay, so this is a simple definition for simple harmonic motion. Now let's see what this whole thing is. So here you have different examples. Okay, the first one is a swing example. Okay, you can see that the swing is following the same path. Okay, to and fro it is going in the same path. In the second one, what you are having is a spring and it is attached with a mass. So this is moving only in this path. So it's a to and fro motion. It is also a simple harmonic motion. And now when you consider this car example, so what is happening is that it's a monster truck, I guess. So what happens is that you can see the shock absorbers of this particular wheels. These shock absorbers are moving in perfectly a straight line. To and fro they are moving up and down. Okay, so that's also a simple harmonic motion. I'm not talking about other motions, I'm just talking about the motion of the spring. It is a simple harmonic motion, up and down in the same path. Similarly, this is our grandfather clock. So what is happening here? Here the pendulum is moving just like the swing case. It is following a particular path. It is going to and fro in the same path. So these are few examples for simple harmonic motion. Now we need to know why we need all this, why we need to learn the time period, the frequency, what is the importance of it. The very first thing, it is the resonance. Okay, this term is very familiar for you. When does the resonance happen? When the frequency of the exciting force matches with the frequency of the object, resonance happens. Okay, so let's see what it is. So here what we have are two tuning forks. Okay, tuning forks, and what we do, when I excite the first tuning fork, here you can see this, the second one is also getting excited, and the excitation of the second one is due to the frequency of sound. When I'm hitting this, some frequency, the sound is generated with some particular frequency, and that particular frequency created matches exactly with the tuning fork of the same dimension on the other side. And in the second part, what we have seen is that we have increased the length of the second tuning fork. Now what happened? That exciting frequency is not able to make this tuning fork move. See the difference? When it was having same, so the frequency developed is resonating frequency, and the other one also moves. When I change the height of this tuning fork, it's natural frequency got changed and it is not vibrating with that particular frequency of voice or the sound. Okay, another example is here. So you can see here there is a glass and some sound is generated which is making it vibrate. Okay, and when the was frequency of the sound exactly matched with the frequency of the glass, what you can see is the process called as resonation, and it breaks. So this is the problem with resonance. So when we think about designing some object, we need to take care of this resonating frequency. The operation frequency, if a machine is there, a machine will be operating at some frequency. If that frequency happens to match with the natural frequency of the machine, then the machine may undergo catastrophic damage. You can see the case of that glass example. Okay. Now, so same thing, why we need natural frequency and time period, why we need to study about those. So I'm giving one example here. This is a bridge. Okay, it's a suspension bridge. You might have seen bridges like this. So this bridge is basically suspended using cable. So what you're seeing there is the effect due to wind. Okay, in that particular bridge, what happened is that a wind blew at a particular frequency which accidentally matched the frequency of the natural frequency of the bridge, and resonance happens and this bridge collapsed. Okay, so they might have considered all other factors like the loads coming in the bridge, the span, everything they have considered, but they didn't thought about such a frequency wind. It created resonance and the bridge collapsed. Okay, so that is very important, that we should be very careful about this time period and natural frequency of the structure we are constructing, and also of the frequency that is going to get excited due to the operation. Okay, now here is another example, a helicopter. Okay, this was a testing done with the helicopter. So here what happened is that when that fan of the helicopter started to rotate, it generated a frequency, and that frequency happens to be matching with the frequency of the natural frequency of the helicopter. Resonance happened, and you can see it completely got destructed. So this is why we are focusing on the study of natural frequency and time period of different objects or structures, so that we can avoid such catastrophe. Now, how to quantify simple harmonic motion? So that's what we are going to try here. So this figure, we are going to use this concept again when we are deriving the expression. So I'm just telling it this. So what you have is a spring. Okay, this is the unloaded position. So when the load is not there, the spring will be like this. Now I'm starting my experiment by pulling this spring down to this point. Okay, and when I leave it, it goes back and it keeps oscillating. Okay, so what is the time period? Time period is the time for completing one cycle. Okay, or one oscillation or one repetition. So you can see here, this particular ball or the mass, I'm taking this as a time 0. Now it goes there, and the time it takes to return back to the original position is considered as time period. So here you can see that it's this is a motion of the ball. When the ball was here, it was time 0. The time is moving, and when you can see that when it again comes back to the original position, this is the value of time. So this particular amount will be the time period for this particular oscillation. Okay, and this depends upon the spring and also the mass attached. Okay, that is the spring constant and the mass are the two parameters which influence the time period. We will discuss in detail and we will derive the expression for that, and you will know how this mass and spring constant are connected to the frequency. Similarly, what is frequency? We have seen time period. It is a time for completing one cycle. What about frequency? Frequency is basically normally represented in the unit hertz, and it is the number of cycles per second. If you are considering 1 second interval, how much cycle does it complete? That is the frequency. So you should be very clear about time period and frequencies are two parameters, and you may observe that time period is the inverse of frequency. If you do 1 by frequency, you are going to get time period. 1 by time period is frequency. Fine. And here you have seen two terms, A, plus A and minus A. This A is called as amplitude. Okay, we are going to repeat that again, don't worry. Amplitude. Amplitude is basically the displacement the spring can have from its neutral position. This is the neutral position. The center point is the neutral position. From this neutral position, it is how far it displays. So you can see here it displays up to this in this direction, and from this neutral position it displays up to this point in the other direction. So the total amplitude, you can see the total movement is 2a, that is a plus a, and it can be seen that to one direction is plus a, the other direction is minus a. This a is called as amplitude. Okay, so with this basic idea, we are going to derive the expression connecting time period, frequency, spring constant and mass. Okay, so now you know what is simple harmonic motion, why we need to study it, what is resonance, and we are going to derive the expressions. So let's do that. So here we are considering a spring. Okay, so we are going to establish the relationship between time period, natural frequency, the displacement, mass, stiffness. We are going to connect all of them. So it's a simple experimental setup will help in calculating this particular relation. So I'm considering a spring. Okay, what I have is a spring, and to the end of it a mass is attached. Okay, a mass is attached. Let it have a mass of m. Now this is resting on a smooth horizontal plane. That's the assumption what we are making, which means that there is no frictional force. We are just neglecting the effect of frictional force. So this is the situation. Now what happens? So what I am doing is I am applying a stretching force. I'm going to apply a stretching force, and I will pull this mass to an initial position, say here. Okay, this is the initial position, and let this be at a distance of x. Okay, now when I do that, so automatically what happens is that this spring also get stretched and it comes here. So for time being, let's assume this as a spring. Okay, so I extended it and I kept it in this position. That is what the condition is. Okay, now we need to analyze the different forces in the system. So if you consider this particular force system, I'm plotting the different values in here. So I'm having the mass, okay, which gets converted to weight. It is acting downward, and there is a normal reaction acting upward. What about the other forces? If you observe this spring or this rubber band, what you can find is that this force in the rubber band, currently there is no force at all when it is lying like this. Okay, that is in the, when the state was this, the spring is not at all loaded, so there is no force. Now as I start to elongate it, force develops. If I'm elongating it only to a short extent, okay, the force developed is very small, right? Now if I'm elongating it to a larger extent, what happens? The force developed is very strong, which means that the force developed in a spring, F is proportional to the extension or the displacement I applied in the system. Okay, F is proportional to X, and this proportionality constant is very familiar for you. You will know it as K, which is called as stiffness or the spring constant. Okay, those are the two names we normally associate this K to, or this proportionality constant, stiffness or spring constant. So you might be familiar with this term from your school days. Okay, this spring constant you might be familiar. The another name for it is stiffness, which is K. And now we need to know the direction. Okay, when I stretched it, the force was in this direction. That's why when I removed the boundary condition, it went back. So the force is in this direction. Basically means that the force is opposite to the direction of extension. Okay, so in this system, the force developed will be in this direction, and it depends upon the magnitude of X and the spring constant, so that is Kx. So that's what the force is in this system. And now we can see that this object was initially here, and it got stretched in this direction. So what is the direction of acceleration? The object is moving to the right, so the direction of acceleration is to the right, right? Acceleration is to the right because it is moving to the right. Now I'm going to write the D'Alembert's equation that we have already seen. So for that I need some sign convention. I'm considering a coordinate system. This is x and this as y. And these are my positive directions. Positive x is to the right, positive y is upward. Now I'm trying to write the expressions. So first I'm trying with sigma fy equal to nay, the D'Alembert's principle. So in here, what is the magnitude of ay? That is acceleration in the y direction. This mass is resting on this floor. There is no vertical movement as the floor is perfectly horizontal. That's what our assumption is. So what happens? The value of nay becomes 0. So which gives me sigma fy, positive is upward. So n minus mg equal to 0, which implies n equal to mg. So that's a observation I'm getting from sigma fy. Now I'm trying sigma fx. Okay, sigma fx equal to max. Now what about ax? Ax is the acceleration in this direction. We know that acceleration is given by differential of velocity or rate of change of velocity or second differential of displacement. So this can be represented either as v dot, that is the first differential of v, or the second differential of displacement, that is x dot. So all these representations are valid for acceleration. So I'm using this x double dot convention. So what will I get? Sigma fx. What are the forces in the x direction? There is only one force, which is kx. Positive is to the right direction. That's what my assumption is. So this is minus kx. So I will be getting minus kx on the left hand side. And what about the mass? Mass is m, acceleration is x double dot. Okay, so I got this relation. Now I'm just reconstructing by taking every term to the right hand side. I'm going to get mx double dot plus kx equal to 0. And in this can be rewritten as x double dot plus k by m times x equal to 0. And this is a very important equation when we deal with dynamics. Okay. And in this there are different parameters, right? X double dot. What is the x double dot? X double dot is the acceleration. Okay. X double dot is the acceleration, k is the spring constant or stiffness, m is the mass, and x is the displacement. Now let's try to solve this. So what kind of equation is this? So if I'm writing this particular equation in a more familiar way for you, this expression is basically d square x by dt square plus a constant k by m x equal to 0. What kind of equation is this? This is generally known as the differential equation. So in mathematics you have learned how to solve or how to get the value of x in case of a differential equation. So what we are going to try here, we are going to have a small experimental setup so that we will be knowing what is the best fit equation or expression for x. So what I'm trying is a case like this. I'm hanging a mass on a spring in a setup like this. So there is a weight at the bottom and it is hung on a spring, and I will be pulling this down. Okay, when I pull this down and when I release it, what happens is that this mass will go up and down and it will oscillate. Okay, it will oscillate. So it's like I have a spring kept like this and I'm applying a weight. It will go down and come up. So I'm putting it in this way so that it will be easy for you to see. So this is the same spring. Now because of the weight, it will oscillate. It will go down and it will come back in a straight line, right? Now I'm going to use that property and I'm going to include the component time because it is with respect to time. And I want to visualize how it will be working. So for that I'm using a simple setup. Okay, so let this be the movement of mass. So the mass is moving up and down, right? It is moving up and down in this fashion because of the
initial stretch I applied. Now to understand the effect of time, what I'm going to do is I will be simply moving this in the x direction or in this direction, so that I'll be knowing what is the effect. Okay, I'm just trying to visualize it. So this will be moving like this and the paper will be moving like this. So let's see what happens. So when I move the paper and keep the spring oscillating, what I'm going to get is something like this. Okay, this is not the perfection because there are errors in the movement and the movement of the pen. So if I'm doing it really slowly with the spring having very low stiffness, the shape of diagram what I'm going to get is something like this. Okay, if both the system and the x or the time component is applied correctly, what I'm going to get something like this. And what is this? Are you familiar with this type of curve? This type of curve we generally call as the sine curve or the cosine curve, right? Sine curve or cosine curve. Do you remember that? What does a sine curve look like? We know that sine 0 is 0. Okay, sine 0 is 0. Then what happens? Sine pi by 2 is 1. Sine pi again 0, goes here, and it continues. So you will be getting a graph like this. This is our sine curve, right? This is our sine curve. What about the cosine curve? Cosine curve is also the same. The only thing is that there's going to be a phase difference, right? There will be a phase difference. So for a cosine curve, cos 0 is 1. Then this is cos pi by 2. Cos pi, which is minus 1. It again goes here. So here the cosine curve will be looking something like this, which is exactly same, only difference is that there is a phase difference. Okay, so when we suggest an expression, that expression should take care of this phase difference. So we'll be adding one component to take care of the phase difference. So you can either use sine curve or use cosine curve. You're going to get the same expression in the end. So here I'm going to stick on with the cosine curve. So let's see. So what I'm going to do here, I'm going to suggest a expression. Okay, so I got it as a cosine function. So I'm putting it like this: cos omega t plus phi. This phi is to take care of the phase difference. And in here I am writing the value a constant a, which is basically called as amplitude. Okay, the name for a is amplitude. So what is amplitude? That's what we are concerned of. What is amplitude? So let's see what it is. What is the maximum value of this function cos omega t plus phi? The maximum value is 1 because the cos varies from minus 1 to plus 1. So what is x? X is the displacement. So this x will be moving. So I'm considering this setup. So I stretched it and I leave it. So what happens? It goes here and it goes all the way to the other direction to a distance x. Considering this as 0, it will go here. Okay, this is minus x, this is plus x as it comes back. So x is the maximum distance this or the maximum displacement this mass is having. So the range is from minus x to plus x. So this amplitude a, so when this becomes 1 or minus 1, this amplitude represents the maximum value. Okay, that's the amplitude. So when we say amplitude, that is the maximum distance. It is going to move to the right or to the left, up or bottom. Okay, that's amplitude. Now we are going to look into this one. Okay, cos omega t. So the phi is the phase angle. So we already said what it is. Now we are going to think about omega t. So a cos function is having the maximum value, that is 1, when omega t is 0 and omega t is, what about the other one? 2 pi, right? So we have the function. So here you can see this is the value 0, this is pi by 2, this is pi, and again this is 2 pi. So the maximum value is for 0 and 2 pi, or else you can see it here. When it was here, I'm considering this angle as 0. Okay, it was this case, it was this initial case, the maximum amplitude. Now it goes like this and reaches here, which means it becomes pi by 2. Now it again moves, it becomes pi, so the value is minus 1. And then what happens? It comes back, it reaches here, and it comes back at this initial position. So you can see that the time, okay, what is this time called? When an object started from here, went there and came back, it is considered as one cycle or one oscillation. So one cycle, the time taken for one cycle or one oscillation is called as the time period. Okay, so how much time will be required? We'll be requiring a time which is equal to 2 pi by omega, right? If omega t is equal to 2 pi, t equal to 2 pi by omega, which is our time period. Okay, so we got this. Now I'm going to try to get the value of x double dot. X we already have. This is the x function. Now what I'm going to do is I'm going to try fit this expression in this equation, and I'm going to check whether it is working perfectly fine. So I'm going for x dot, that is first differential of x with respect to time. When I differentiate it with respect to time, there is a t, the t comes out, so no, there's a omega t, so differential of omega t with respect to t is omega, so I'll be getting omega. What about the a is a constant, differential of cos is minus sine omega t plus phi. Now what about x double dot? I'm differentiating it again with respect to t. So another omega comes out. So omega square a, then this sine is cos. So cos omega t plus phi. Okay. And if you are observing, you can find that this term that is written here, okay, it is the x itself, because x is a cos omega t plus phi. So with this, I can rewrite this above equation as x double dot, which is minus omega square x. So minus omega square x plus k by m times x equal to 0. Okay, and if I'm taking this omega square x to the right, I'm going to get omega square x cancels out. What I will be left will be k by m, which implies omega is equal to root k by m. Okay, this is another important expression that you should remember. That is omega is equal to root k by m. And what is the time period? We have the expression for time period. The time required for completing one oscillation on one cycle of rotation. Right? What is the one cycle? It is the value t, which is 2 pi by omega. We have already established that. So I'm going to calculate the time period, which is 2 pi by omega. And omega is this. So what will be this expression? This expression becomes t equal to 2 pi root. This is k by m. Inverse of it is m by k. Okay. T is equal to 2 pi root m by k. And this is an expression which you cannot forget if you want to become an engineer. Throughout your life, you will require this particular expression. The time period is equal to 2 pi root m by k. And we will be familiar with another term which is called as, so this, what is the unit of this? It's measured in seconds, okay, the unit of time. And there is another unit which we are familiar about. It's hertz. What is hertz? It is the frequency. What is frequency? If you are putting frequency as if I'm putting frequency as n, it is given by 1 by t. Okay, the inverse of time period is the frequency. Okay, this is the frequency. Okay, so you have the frequency as 1 by t, and you have the time period. Okay, time period is the time required for one complete cycle or one complete oscillation. It is t equal to 2 pi root m by k, and frequency is 1 by t. So these are the take home from this particular lecture. One is this very important equation of dynamics, that is x double dot plus k by m x equal to 0. The expression for time period t is equal to 2 pi root m by k, and the frequency, which is inverse of time period. So what will be the expression? N equal to 1 by 2 pi root k by m. Right? Now let's analyze the different terms. So what time period depends on? Time period depends on, this is a constant, m and k. Whenever the mass increases, the time period increases. So you can see here, if I'm hanging something which is having a larger mass, what will happen? It will be taking a lot of time to come back, right? So it depends upon the mass. Okay, if it's a huge mass, it will go down a lot and it will take more time to compact, which means it depends upon the mass of the object that you are attaching to the spring. And the second one is K. What is K? K is the stiffness. So you can see here, if I'm using this as the spring, this much time is required for it to compact. But if I'm reducing the, I'm making it 2 times, right? I reduce the length. Now what happens when I reduce the length? The stiffness of the spring increases. For the same load or the same mass, it comes back really fast. Okay, so whenever you are using a spring which is very stiff, it will come back very quickly. But if the stiffness is very large, a value or magnitude is very large, then it will take a lot of time, which means the time period is inversely proportional to the stiffness. That's what this particular expression is. Okay, so you are going to have problems where you will have to calculate either the omega or the time period or the frequency. So you'll be playing with this particular equation. Different parameters will be given and you want to calculate this particular thing. And I forgot to mention one thing here. We are considering the spring as massless. Okay, the mass of the spring compared to the mass of the object what we have attached at the end, it is negligible. So we are ignoring the mass of the spring. Only we are considering this body or the object is having a mass m. Okay.